Morning, welcome back. Happy Friday. Today we are covering something called the definite integral. We've got 2 days of new material left coming up and then 2 review days. And then our final exam will be here before you know it. I will hand out the last project on Monday and the last quiz on Wednesday. Any questions on the schedule? Yes? What is this 5? Yeah, it's lessons 37 through 39, so 3 days of stuff. Other questions? Okay, so let's jump in here at the top of 64. In this class, we introduce the definite integral as well as the integral symbol. We also discover that the more rectangles, the better. We'll see that momentarily. In the last class, we estimated area under a curve. And the reason we cared about area under a curve is that if that curve happened to represent the velocity of one of our zombies, then what did the area under the curve represent? The total distance traveled, right? That's what the area was. So apparently area under curve is sometimes something that has an application. Turns out it's got lots of other applications that we'll see in Calc 2. And the way that we find area under a curve, or at least approximate it, is to draw some rectangles. So in this picture here, I have drawn 4 rectangles. And in particular, we're going to call these things right rectangles. Not right as in correct, but right as in not left. And the reason that these are right rectangles is that, for example, in this very first interval here, to determine the height of that rectangle, we went to this point, which was the right-hand point on that interval. And we went up to that height, and then we completed the rest of the rectangle. And in the second interval, which point did we pick to determine the height of the rectangle? The right-hand endpoint. And so these are 4 right rectangles. Just as well, you could pick 4 left rectangles. You could pick midpoint rectangles. We'll draw one here in this last space. Suppose we look in this last interval. We're going to draw a brand new rectangle. It is not pictured yet, based on the height being at the midpoint of this interval. So we go to the midpoint. We go up to the curve, say it's right around there, and then we complete the rectangle at that height. We would have a rectangle that is smaller than the one that is pictured there. Everybody see it? Okay, in the last class, what's that? Oh, thanks. In the last class, we saw this messy formula. Let's talk through it again to make sure it seems reasonable. We came up with some notation last class. We said that we were going to call the width of each of these rectangles delta t. Was chosen to be the same width for every single one of these rectangles. So delta t for a change in time. And then the height of the rectangle, well, we said it's based on the, like each of the points. And so if you remember, we called this point right here T0, and this point here was T1, and this was T2, and this last one here was T sub n, because n was the number of intervals. And so, for example, for the orange rectangle, which one determined the height? T0 or T1? Was T1. And that height is simply the function value, the y value at T1. And so this height right here, I'm going to draw it like this. That height is f of T1. Agree? And then the next height, the green one, is this thing right here, which is f of T2. And what's the very last height? In this one. That's f of Tn, the very last one. And so the sum of the areas of those rectangles is delta t times f of T1 plus delta t times f of T2 plus etc. And then the last one is delta t times f of T sub n. And so that is written there in all its glory. Okay? So that right there represents the sum of the areas of the rectangles. And it is approximately the area under a curve. It's not going to be exact. I can see that I've overestimated. Like if I'm just thinking area under the curve is what I'm after, that first rectangle overestimates. It grabs some space that is not under the curve. The second rectangle underestimates. It misses some space that's under the curve. So it's going to be an approximation for the actual area under the curve. And we call this thing here a Riemann sum, named after George Bernard Riemann, a mathematician. I think he was like late 19th century, early 20th century. Yes, all the delta t's are equal. Yeah, we define it that way. Okay, so we can abbreviate that thing. Come on now. We can abbreviate this thing right up here using sigma notation. Do you guys remember that from the regression project, the data project? Because all of these terms have a very similar format. So let's see if we can capture what's the same and what's different. Okay, what's the same in all of the terms, like separated by these plus signs? Well, there's a delta t, and then there's a times, and then there's an f, and then there's a t, and the only thing that changes is that little number down there, right? It becomes 1 and 2 and 3 and all the way up to n. And so let's replace that specific number with a generic letter, and I want to pick the letter that's on your page. I. Let's call it I. And then we say we want to add all of these things up, and so that's where the Greek sigma comes in. Sigma for sum, S, sum. And at the bottom, we tell the reader what the starting value of I is. What is it in this very first term? It's a 1. And then at the top, we put the ending value of I. What is it? It's n. And so that is the compact way to write down what's highlighted up there in yellow. It represents exactly the same thing. This is just a random aside, but maybe 10 years ago, there was a hip hop artist named T.I. who had like one really popular song. Do you remember? Like when that song came out, I was like, all I could think of was this like sigma notation thing here. I was like, he is paying tribute to Riemann sums with this, his name. I am a nerd. All right. Okay, so we got that. Number 5. What can we do to get better and better approximations for the exact area under a curve? Okay, take a look. First, let's decide whether these are left rectangles, right rectangles, or midpoint rectangles. Let's pick one kind of in the middle. This one right here. What point in this interval down here is the one that dictated the height of that rectangle? Was it the left point, the right point, or the midpoint? That's a midpoint. Right? These are all midpoint rectangles. Okay, so you get, again, you're trying to approximate the area under the curve. That is a hard problem, so we make it easier by drawing rectangles. What can you say about the approximation using 5 rectangles compared to using, I don't know, 10-ish, and then I can't tell how many's over there, 20? What do you think about the approximation as you use more rectangles? Yeah, the more accurate it is. More rectangles, it gives you more accuracy. So here you go, as n is the number of rectangles. As n increases, the area of the rectangles approaches the exact area under the curve. All right, so putting it all together, here is the, whoopsies, come on. The full-fledged, hardcore, no messing around definition for the area under a curve. I'm just gonna jump to the symbol. It says that area equals, all right, we're just gonna go piece by piece here. This is the width of a single rectangle. This is the height of a single rectangle. When you multiply the width by the height, what are you getting for that single rectangle? The area. This says add up the areas of all of the rectangles. Right? This says you want how many rectangles? Infinitely many, right? If 20 is better than 10, then infinitely many is better than 20. And so that right there is our definition for the area under a curve. We're defining area under a curve because if you think about it, like there's a small collection of figures whose areas you know formulas for, like you know the area of a triangle, you know the area of a rectangle, you know the area of a circle, maybe you know a couple of other ones, but it's a pretty short list. So here we are defining the area of a curvy shape. We're defining it by saying we're going to use infinitely many rectangles to approximate and then just define the area. Daniel? Yeah, the same formula for delta t we came up with last class. We're not going to actually end up using that b minus a over n, but yes, that is what it is. Okay, so next page. So this formula isn't something you need to memorize, but calculating area under a curve is something we'll do many times in the last week here, and then a bunch next semester in Calc 2. So we'll use some new notation to avoid having to write the formula above, because that's kind of a mess to write down. And so all we're going to do is come up with new symbols, shorter symbols than the ones that are on the previous page, okay? And so that thing on the previous page, which I will highlight here, this is a copy of what was on the previous page. All we are saying is that we are going to use these symbols on the left instead of the symbols on the right. And those brand new symbols on the left, it's the first time we are seeing something called an integral. And that curvy symbol in the front is the integral sign, all right? So there's nothing complicated or crazy or outlandish about those symbols on the left. It is just a shorthand way of writing all the stuff on the right-hand side. So if you see this thing in green, what you think is, oh, Ian is just asking me to find the area beneath the x-axis or t-axis and the curve, looking for the area under that curve, but between two specific numbers, x equals a is the left-hand thing and x equals b is the right-hand thing. Okay? So those symbols just mean find the area under a curve and above the x-axis between two x's. Okay, so some vocabulary here. That symbol is called a definite integral. The numbers on the integral sign are called the limits of integration. That's the a and the b. They'll be numbers, not to be confused with all of the limits we've been calculating this year, including that limit there as n goes to infinity. It's an unfortunate choice of word. Anyway, those are the limits of integration. And then the function itself, f of t, is called the integrand. Kind of like you have a radical and the thing inside is called the radicand. You have an integral and the thing inside is called the integrand. Typically we use x as our independent variable, not t like it's up above. So our integrals will often be of the form this thing here, just x's instead of t's. And the two things here, they look quite similar to me. I mean, look, I see an f of ti here and then an f of t. And then it's multiplied by, and then there's a delta t here for a little change in time, and then there's a dt here. It's supposed to see, you know, it's the same d, right? Just Greek delta versus our d. Okay, for example, what does this symbol right here mean? Let's see if we can come up with a sketch to identify what it means, and then we'll approximate it by hand. Okay, so this is the integral from 0 to 3. I'm reading this for the first time. Some of you have seen it before in like a previous calc class, but if this is your first time, here's how we read it. This is the integral from 0 to 3 of x squared dx. It's not the integral times, it's the integral of, just like sine of, cosine of. Okay, so what does it mean? Well, it means that there's a curve. What's the function in this case? X squared. Okay, so we draw the parabola x squared. And what are the important x values for this particular one? 0 and 3. Those are given to us. So x equals 3, we'll say, is out here. And x equals 0 is where the parabola hits the origin. And all of those symbols, the brand new symbols, just mean the area between the curve and the x-axis, and between 0 and 3. And so we can shade in this area. It is just this space right in here, okay? So whatever that area is, that's the value of the integral. That's what we're after. And again, that's a hard problem because I don't know, I don't have any formula for the area underneath the parabola. I have very few formulas for areas of curvy things. So let's just get a ballpark approximation here in the activity. You'll use technology, your calculator, to get a better approximation, and then next class we'll actually use calculus to get the exact answer. Let's go ahead and approximate this by drawing something straight. How about that straight line? And what we're going to do is find the area of the triangle that's drawn now. That purple line, and then the orange line, and then the x-axis. You see the triangle? When we get our triangle area, is that going to be too small or too big compared to the actual green area? It's too big, but it's a first step. Okay, so what is the height? Well, I don't know. How do you find the height? Yeah, we got to plug in the value, right? Like you have the formula there. So we plug in 3. This is the point 3 comma 9. And so the area of my triangle, half base times height, half of base is 3, height is 9, right? So we get 27 over 2, 13.5. So just for practice, go ahead and copy all of those symbols. And our first guess for this one is that it is right around 13.5, but it's definitely less than 13.5. 13.5 is the triangle. The integral symbol is just the green area, which is smaller than the triangle's area. Megan?
that area,
Mm-hmm.
you have to like make any notation of the fact that the x-axis is on top of it?
That's a great question. So in the activity, it talks about stuff going below the axis. So for example, this picture here. So there's a difference between, I'm just going to read what's there. So let's just wait until you get to the activity and you will read what's there. I think it's well written. I wrote it. All right, so in the beginning of the activity on the next page, there is some graphing calculator stuff. I've got a whole bag of graphing calculators. So if you don't have one or a convenient, even if you have like an app on your phone, you might just grab this because I'm telling you what the syntax is and I don't want you spending time trying to figure out what syntax is on your phone. So scientific calculators are not going to work for you today. Come up and borrow one if you don't mind leaving your phone and then I will walk around.